Okay, wonderful. Again, if people have difficulty hearing online, I can hear the speakers are working too. Just let me know and we can start over. So yeah, so as the introduction, I'm here at the University of Illinois, and really I'd say split in my job of faculty in material science and engineering and director of the materials research lab. If you have materials characterization needs, MRL has some very excellent resources. If you're having challenges accessing it, let me know. We're also the administrative home for Amtel. So if you use Amtel for mechanical property measurements and you find something there isn't meeting your needs, let me know. You're my eyes and ears when things aren't going right. Okay, so let's start with batteries. So let's, can we close some of that at the top? Let's see here. Okay, under more. Right for you. This is one. Okay, perfect. If they pop back up, I'll go do it. Don't worry about it. So wanted to talk a little bit about the invention of batteries briefly. So it was discovered in 1870. Galvani and his wife, they don't give her enough credit here, discovered that the muscles of dead frog legs twitch when struck by an electrical spark. This was sort of in the early days of electricity, the Ben Franklin, I'm going to put a key on a kite and get a spark. That's probably a true story. He's very lucky he didn't get killed doing that, but that's a different story. But it was soon afterwards discovered the frog legs convulsed when brass hooks attached to the spinal cord into an iron railing. So now we have two dissimilar materials. If I have two dissimilar metals, it turns out the two metals like electrons a little bit differently, and you get a current. You may have noticed this. If you have a metal filling and you bite down and there's a little bit of aluminum foil, you may feel something in your mouth. Same thing, you have made a battery. And so this so happened, his wife was an invalid and on one occasion wished to make some broth of frogs. Much to her astonishment, that on bringing a knife near one of the legs of a frog, they were convulsed. This is one version of the story. I'm not going to say how accurate any one of these versions were. I wasn't there in person. But at this point, they thought it was animal electricity. They thought the animal had electricity left. They thought that we all had electricity in us, and the metal was pulling the electricity out. It was not for a little while that it was recognized that, in fact, it was not that at all, but rather the other way around. Oops. Yep. Okay. But actually, not that long after it, Volta, an Italian physicist around 1800, so only 20 years after this, developed the voltaic pile, which basically was to have two dissimilar metals with some brine or salt in between this. This was the voltaic pile. Without the voltaic pile, we would not have had the telegraph. So sort of if we think about the evolution of modern communication, this electricity was because we recognized how to build a battery. And so now, over 200 years ago, you now could have batteries, and they were, science demonstrations, etc. Of course, we have the volt as the unit of electricity after Volta. You can do this at home. So if you feel like going home tonight and you get a lemon and a piece of steel and a copper wire and touch it to your tongue, you'll get a voltage. You can find YouTube videos where people create electricity using 10,000 lemons, and they generate and they make a spark, and they make some video and get views, I suppose. You can of course buy these potato battery, and you can run a clock until the potato rots away. Fortunately, these draw microamp current, so you don't have to have a very good battery. I don't think we're going to drive vehicles around with potatoes with pieces of metal stuck in them, but it gives you the idea that really to have a battery, all you have is you have two materials where one of them likes electrons a lot more than the other one, and they're separated so that something can go in between them, typically ions, but not electrons. And so that's basically what a battery is. This is no different than, in fact, you can charge this battery if you go the other way. For a little while, you can plate some copper and dissolve a little bit of the iron, but obviously not significantly. Okay, so what do we have in the battery here is we have indeed that you have a material that likes electrons, a material that does not like electrons as much. So this is our lithium-ion battery. And the key here is that when I am discharging, so when I'm discharging a battery, what's happening? Well, I have lithium, and it's in lithium zero. So lithium zero means that it has all the electrons at once, and that lithium zero is basically living between sheets of carbon. This is our normal battery. I want power from the battery. The lithium gives up an electron, and the lithium moves through and it goes to the other side. So you can think of this as basically two parking garages for lithium. In this parking garage, it's the high energy form of lithium. In that parking garage, it's the low energy form of lithium. And when it moves between those two, electrons move through the circuit. When I charge the battery, the opposite happens. The lithium goes this way, goes into here, and comes out and goes to the high energy form. Electrons go through the circuit. If you ask me what is the biggest fundamental problems with batteries today as compared to, say, fuel, so if we think about a vehicle, you have an internal combustion engine, you take hydrocarbons, which is carbon and hydrogen, that is oxidized, forms CO2 and water. Basically, the storage tank doesn't weigh very much. You have a tank, and the engine mass isn't that high if you have a high efficiency engine. In a battery, for one lithium atom, this is in your cell phone battery, which is the easiest one to explain. For me to have one lithium, which gives me one electron, it turns out I have another lithium that doesn't do anything. I have two cobalt atoms, which are pretty heavy. I have 4 oxygen atoms, and I have 6 carbon atoms. And that's just to make the 2 parking garages here, and that doesn't include anything else. So in a modern lithium-ion battery, only a single-digit percentage of the weight is actually the stuff storing energy. The rest of the weight is just the infrastructure. It's probably actually not that different than a parking garage. If you calculated the mass of the cars and the mass of the parking garage, on a mass basis, it's not a very efficient way to support vehicles. Well, same thing here on a mass basis. This is really inefficient. So to get to the end of the story, what the world is trying to go to is batteries that maybe store the energy as lithium metal. And on this side, don't need to have a bunch of heavy metal atoms for each individual lithium. So if we could do that, we could have 10 times more energy in the battery. So where a battery is today is maybe 10% of where it should be if we could only figure out all those problems in a way that doesn't cause a battery to explode. I should actually point out those very, very high energy batteries that I'm mentioning have been around since the 1970s. The problem is that they explode on a somewhat regular basis. So multiple companies have tried to sell batteries where they get rid of all of this and they just have lithium here and sulfur over here, for example. And the problem is that after a few hundred cycles, on a very random basis, they explode catastrophically. And so there have been a Japanese company that did this. They were selling them, everything was great. And then after about 4 months, all the batteries started to blow up. And so obviously they pulled it off the market. So we know it can be done. The other thing, of course, to keep in mind, not that I need for this group, but when I talk to sort of materials people, they're like, oh, you could do all this. And I'm like, okay, I could do all of that. But I have to do it at this scale. I need 90,000 watt hour. That's 90 kilowatt hour. That's like just an EV battery. But that's, 500 kilograms or more of material. And so, I'm not going to grow that in my lab using like 1 atom at a time and things like that. So scalability matters. So where are we? I mean, we see these now around town, and I'm sure you're familiar, and some of you may drive EVs or have driven them at some point. There's nothing new about this. This is Thomas Edison and George Meister and the Studebaker in 1909. It had a 50-mile range. Not bad. The problem was that it's top speed was 11 miles an hour, but in 1909, that wasn't bad. It turns out that I haven't updated it, but it turns out the cost wasn't much difference. This cost $35,000 in 2024 dollars. So electric vehicles have cost, let's just say, $50,000 for the last 100 plus years. And then, of course, these are more modern ones, and every year or two I have to remember to update the pictures. Back up one. But these are ones I probably saw at least 3, if not all 4 of these just coming up here today. So, and again, the cost is not that different than the Studebaker electric runabout. So there's an interesting case study you're probably familiar with, and this is light-duty vehicles, which of course is one of the big problems right now. It's light-duty vehicles, I would argue, it's a solved problem. Maybe at the margins there's issues, but it's not the big problem. And the existence proof, of course, is Norway. Just last month, in August, battery electric vehicles was 96.9% of all vehicles sold in Norway. So for all you hear about people saying electric vehicles don't work when it's cold, electric vehicles don't work when cities are far apart, I haven't been to Norway, but I've looked at the map. I think it's a place where the weather gets relatively cold, and I think it's a place where there's some cities which are pretty far apart. So to me, that's enough of an existence proof that there may be some financial issues, but US has twice the population density of Norway. The average temperature in Oslo, it's a little cooler in the summer, it's a tiny bit warmer in the winter, it's not that different than Chicago. And Norway's a little bit richer than the US. Basically, they sell the world oil. That's a whole different value judgment. But by doing that, they've been able to do that. But basically, in 10 years, basically all light-duty vehicles. So in Norway, about 1/3 of all light-duty vehicles on the road are electric, about 1/3 are diesel, and about 1/3 are gasoline. And if we look at the trend lines, and assuming a light vehicle of 10 to 15 years, they'll be there. Heavier vehicles is a different problem, and of course that's because now you have a lot more issues with mass, the batteries get bigger, et cetera, et cetera. Costs are going well, and so I'd actually argue that from a new materials standpoint, cost is sort of an important area. But as a material scientist, we should really be thinking about how to increase energy density or energy per unit weight, because that, in the end, the costs are already coming down and they've fallen some more. But what does this mean? Let's say we get to $50 per kilowatt hour. That means an electric vehicle battery is going to be something like $5,000. And so if the battery's $5,000 and the vehicle's $50,000, it's important to reduce the battery price, but you're not going to gain that much more. There's other parts of the system. So, but it's still pretty heavy. Those numbers, if you look at some of the vehicles, the battery's 1/3 of the weight of the vehicle. So that's a problem. I mean, I don't think we could drive a class, I think it's class 8, whatever the biggest truck is. I don't think we could do that if 1/3 of the weight of the truck was the battery. Then we'd have a problem. So here's our problem. Gasoline has an energy density of 10,000 watt-hour per liter and a specific energy also of about 10,000 watt-hour per kilogram. Lithium ion, this is a log scale, so it looks better than it is, but it's, hundreds of watt-hour and hundreds. Now, it's more efficient, so you get a 3x gain there. But theoretical, for say lithium sulfur, is about 1/3 that of gasoline, and an electric engine is about 3 times more efficient than an internal combustion engine. So if we had batteries of these kinds of chemistries, we basically are where gasoline is on a useful energy basis. So where are we challenged? Obviously heavy vehicle, aviation, agriculture equipment. I was talking to somebody at John Deere, and they're like, look, we actually don't want to compact the field. And so Sometimes we want the tractor to be heavy and we put metal plates on it, but sometimes we don't want it to be heavy. And so the kind of battery you would need to have a tractor out in the field for 4 hours or more becomes weight prohibitive. Electrified rail, we obviously could have a longer discussion. I put this up for aviation. Regional jets, we might just barely be able to do that with today's batteries, but we're nowhere near the requirements for anything other than, say, the flight to Chicago. And even that would be challenged. Okay, so what are the materials? So I'll talk a little bit, I'll get into the weeds a little bit. I'll be happy to answer more questions once we, for those of you, but hey, I am a material scientist. So what are some ways that we can increase the energy? It turns out sulfur, silicon and sulfur store a lot more lithium than graphite. So if we could just get rid of the carbon and replace it with sulfur or silicon, we would do well. The other aspect that's interesting, particularly about silicon, if we got rid of the carbon in the negative terminal, if I burn carbon, I form gas, carbon dioxide. When I burn silicon, I form silicon dioxide, I form glass. And so from a safety perspective, if we could get a lot of the carbon out of the battery, we also would have a battery that would be intrinsically safer and would not require the same kind of control systems. A lot of the weight of a battery now is actually the control architecture for temperature control, flammability, thermal runaway issues. So again, if the battery itself was intrinsically a safer chemistry, we could make it way less because we wouldn't have to surround it with as much infrastructure. And so I'll talk about that. I'll talk a little bit about high voltage, because if you have higher voltage, you get more energy per electron. A little bit about dense cathodes, some designs, solid state. You may have heard of metal air batteries. Here's the idea that you can use oxygen from the air. Maybe they'll work someday. I have my doubts. And the problem is when people say a metal air battery, the first sentence in the paper says metal oxygen. So going from air to oxygen is a non-trivial enterprise, and even a tiny bit of carbon dioxide and a tiny bit of water vapor is a big problem. So metal air batteries are difficult in transportation because you basically have to purify the air, and you have to use the battery for the energy to purify the air. Maybe you can do it, it's going to be hard. This might be more realistic for like grid scale, because now you could have like a large plant and you could purify air overnight when you have more energy. So it's a different calculus. And I mentioned these maybe for aviation, but you can run batteries off lithium metal, lithium air, and this lithium fluorocarbon. So these are primary, but if you hear about battery swapping schemes, there are some ideas we could do electric aviation. The plane would come in and you would unload a big tank of aluminum oxide, and then you would load in a piece of aluminum, and you would take that aluminum oxide and then you would turn it back to aluminum somewhere else. So this is like refueling the plane, but we'll refuel it with sort of pieces of metal. And that might work for aviation. It's probably not realistic for ground transportation. Okay, so silicon, won't worry about this bar for a little while. Maybe I'll just move to the side and maybe it'll stay there. I think if there's a chat or a comment, let's see. Don't worry about it. It's really no big deal. Let's see if it'll. I'll go right there because yeah, I'll just hide it occasionally. Whatever. It's a good break for people to take a breath. Okay, so here's the silicon. So silicon has 10 times the energy as carbon. And so this is if you take the negative part of the battery and you changed it from carbon to silicon, you get 10 times improvement in the negative terminal, which gives you 2 times or so improvement at the whole battery. The problem is, and I know people here know lots about mechanics, the problem is when you put lithium into silicon, it gets 3 to 4 times bigger. So how do you build a battery where half the battery is going like this every time you cycle it? So what did we do? This was sort of our idea, was how about I make a foam? So I make a metal foam and I coat the foam with silicon. And now when I charge and discharge, it goes in and out of the pores, but the whole thing stays the same thickness. It's pretty good, but our metal foam right now weighs too much. This is made out of nickel or copper. I need to figure out how to make this out of, say, aluminum, or even better, out of a polymer or something lightweight that will conduct electricity. So this is a great academic paper, but to become a product, I got to make the metal. The metal needs to weigh less. This is about 15% metal. I need to get down to about 5% metal. But what it does is when you do this right, we're getting, again, remember, carbon is down here at 500 milliamp hour per gram. When things go well, we're at sort of 3,000. We're fading a little bit, but we are getting near theoretical. So the idea works, but the foam needs some improvement. But this is just one example. So if you could get this to work, you get 2x increase in your range for the same weight and volume of the vehicle. Ultimately, we'd really like to think about, can we build a battery like a semiconductor? In fact, since people here know a little bit about pavement, much more than me, obviously, if you look at a battery, the positive terminal of the battery is actually a mixture of inorganic particles, carbon black, and basically tar. So if I look at a positive battery terminal, it has a similar morphology as some granular media. It's made up of ceramic particles, conductive material, and a glue, an adhesive, which is usually just a pitch-based adhesive. And the problem is that there's a lot of spaces here, that nothing useful is happening. If I'm a lithium or an electron, I have to go through some really complicated pathway, lots of surfaces. So what I'd really like to do is be able to make this as like a crystal, a single crystal of positive material, something that separates it, and a single crystal of the negative material, and have the lithium just zip back and forth between those two crystals, and have the crystals have sort of pores in them so things can go through. And in fact, you can do this today if you want to do it in a semiconductor factory, but that means your batteries cost, $10 to $50 million each for a reasonable battery, because you have to make it by cutting up thousands of computer chips. So the physics actually has been somewhat shown, but how to do this in the material science is hard. So what are we doing to get closer to that? Again, this is a normal lithium cobalt oxide cathode. Again, this is the lithium cobalt oxide. The carbon black powders you can see here, and sometimes you see sort of like filaments. Well, that's the adhesive, which is again just typically a pitch or asphalt-based adhesive, is in short. Here's what we do. We electroplate it. So in the same thing, instead of making it on a slurry, we grow it just like you would electroplate a metal from the bottom up. And when we electroplate it, we get a sort of a single crystal, a solid material. And because we grow it from the bottom up, we can actually grow the crystal so it's oriented this way. And these are the fast directions for the lithium and the electron. So now instead of having this sort of random particle, we have highly oriented pathways, and material can go up and down. And this is just a picture on aluminum foil, and here it is on the two sides of the aluminum. And if you get this, you get another 20 or 30% increase at the pack. So the idea again is, maybe you can get the anode and get 2 times, and here you get another time. Now all of a sudden your battery, instead of weighing, 1,000 kilograms, it weighs 300 kilograms. And you're like, okay, well, now I can tolerate that in my vehicle in ways that maybe I can't. So this is sort of this is going to be good for EVs, and at the sort of fringe for heavy transportation. These are scanning electron microscope images. Basically, we're looking at it, And I put this up here because it turns out that the lithium goes really fast through these little sharp edges you see. Imagine like a book. This is like the book standing up and the lithium goes between the pages. Here's the same book and it's turned this way and the lithium can't go through. So this really depends at the details of how are my crystals oriented. If my crystal's the wrong direction, it does not work. And in fact, here, this is C rate. If you're a hobbyist with a drone or something, C rate is how fast you can charge or discharge. 1C would be to take 1 hour to discharge it. And so like a drone battery might say 20C or 50C. That means you can really get a lot of energy out in a few minutes. But if I take it and I orient it the right way, I get basically all the energy out. And if I turn it the wrong way, I basically don't get any of the energy out. So again, this is, again, as a material scientist, this is the kind of thing that we're very interested in. These are all exactly the same material. The only difference the property changes is because we can control how the sheets are oriented. You know, sort of the difference if I was walking to the back of the classroom, I could go this way. But obviously, if there were desks all the way across, then I'd have to really, you know, meander around. Another area you may have heard of are solid state batteries. They've been promised for transportation now for a decade. I suspect they will be promised for another decade. And the question is, you know, do we get there? People like solid state batteries because we get rid of the liquid, which tends to be flammable, with a solid material that might be less flammable. By the way, one of the most popular ones is sulfur-based, and so it doesn't exactly burn, but it gives off a large amounts of hydrogen sulfide gas when it's heated. That may not be better than burning. H2S, forget the smelling part of H2S. At high levels, it's extraordinarily toxic. So there's work to be done. So I think solid-state batteries will be safer, but you shouldn't take that at face value for all solid state and all chemistry. So if your field starts moving into solid state batteries and someone tells you, oh, it's solid state, therefore it is safer, I'd probably say, I'd like to see your test data. Because a few of the solid state chemistries give off extraordinarily toxic compounds when they heat up. So it's worth knowing. But in general, if I have a solid here, I should have a lot longer cycle life because I don't have chemical reactions. Maybe I can make it thinner so I get more energy. Maybe I can use materials that have higher voltages because these liquids can't go as high a voltage. So there's reasons that there's a lot of interest in solid state. You know, conventional lithium-ion batteries are going to top out at about 350 watt-hour per kilogram. And solid state should at least exceed 500, changing nothing else. So, you know, it just basically moves your baseline up. It turns out that the best solid-state batteries right now operate between 10 and 50 MPa pressure. So if you do that, that basically means your battery is living within a hydraulic press. That's not realistic. So we need to reduce that. And there's other problems. And so here's one we've made. You know, our big goal has been to reduce the pressure. And so now we're down to 1 MPa, which is probably doable, but that's still a meaningful pressure. You know, at 1 MPa, we have about 20% fade over 250 cycles. You know, that's not good enough for market, but I think it's headed the right direction. We'd like to get to a half a MPa and 1,000 cycles. You know, then you'd say, okay, now we could make sort of more impact. And here's just some cells that we make. And, you know, this is the reality of the lab. We make one cell, it starts to fade. We make another one, it doesn't. These cells are identical as far as we knew. You know, there's a lot of things that go on that we don't understand yet in these basically solid state batteries. And so this is, you know, more on the frontier area of materials research. Yeah, here's again, this is one of our champion cells. And so we're, you know, as I said, we get to this sort of 80% is sort of what industry would call good enough, but they want 1,000 cycles, not a few hundred cycles. The other thing that's interesting about these materials, and this is actually, if you'd say what makes the solid state hard, it's actually mechanics, which is often the problem in many fields. But basically in the battery, when you move lithium back and forth, the two sides are changing size. So actually, as you take lithium out of one side, it's shrinking. And in fact, then you take enough out and it starts to expand again. The other side's trying to change size. So here you have this battery. The outside doesn't change shape, but inside everything's getting bigger and smaller. And so you'd really like to match it so that as one side gets smaller, the other side gets bigger at exactly the same amount. And so can you do that? That's really hard to do, in particular if your battery's just made up of random particles. So we've been doing a lot of material science work, and can we make a battery so as you charge and discharge it, the two sides cooperate with each other, and one is swelling while the other's contracting? This is down at the atomistic level. So if we look at the atoms here, these are the cobalt. So it's just made of layers of cobalt sheets. But you can see here that the volume expands. So this is charging. You start out here, and then as I charge a battery, I move this way. So as I'm charging my battery, it's expanding, it's expanding, it's expanding, and then it starts to contract. And one of the reasons they tell you, for example, if you want your battery to last a long time, don't go 0 to 100, go 20 to 80, or don't keep your laptop charged at 100%. I mean, they're getting better at this. Don't lose sleep over these sort of things with your laptop. But as this is swelling and contracting, and here it actually undergoes a phase transition, if you stay out of this, you sort of don't want to go into here because things crack, because it's actually changing crystal structure. But if you stay in some of these intermediate regions, you don't put as much mechanical stress on the inside of your battery that can lead to cracking. This is not true for all battery chemistries, I should say. So if you have an electric vehicle and it has an LFP battery, and if you have an EV, you can look up what kind of battery. If it has a lithium iron phosphate battery, going to 100% is fine. But if you have one which is NMC, which is, I would say, tends to be the ones that have the longest range, they don't like going that last 10% very much, and you want to avoid it for a variety of reasons. And they don't like the last 10% as much. So if you have a LFP battery, you can go from 100 down to 10 all the time, and it won't really care. If you have an NMC battery, that staying between 20 and 80 might mean that the battery, I mean, you're going to get a few 100,000 miles probably anyway, but eventually it'll show up. So the other secret, of course, is that when your battery's 100% charged on your phone, they don't take it to 100% just because they don't want it. They want it to fail, but not that fast. I'm sure they haven't figured out exactly the highest profit margin failure rate has been well optimized into your battery. But I have a few students that work at Apple, so I've heard that they're fully aware of how long a cell phone lasts. So what are the details? Well, if you have this crystal that's swelling and expanding, you can actually control the angles of the crystal, because if this side is expanding, this side's contracting. If you go to the right angle, then it won't do anything. It'll stay the same. So there are, you can really use crystal. If you control the orientation of the crystal, it would be like making a material that has no thermal expansion coefficient. So, you can make materials that in one direction have no CTE. It might mean in a different direction they expand and contract a lot with temperature. Here's the same thing. We've basically created one that has no chemical expansion in the direction that matters. And so we can see when we cycle the cell, we can make one. This is a lot of details here, but this is basically the change in pressure as you charge and discharge. we can orient it so that there's no change in pressure in the cell. So what this basically means is that as the cell charges and discharges, the expansion of one side exactly matches the contraction of the other, and that helps reduce cracks, defects, voids, and lots of other problems. And what that does is, a big problem is you actually get voids. And you get a void here if the material's trying to expand. And so you can make it so that basically there's just enough pressure that you don't get void formation. And we can go over the details later, but these are just a bunch of charge and discharge at different currents. And this is a map that basically, if you do it right, you can go all the way up to here. You can go to, 7 milliamps per unit area, where if you do it wrong, you're much lower. You're only, 4 or 2, depending on the orientation. So it's basically playing with the internal mechanics of the battery to make it work. And this is, again, the details. We just had the paper accepted. We're happy about that. So if you're really interested, I'll send you a version of it if you want to spend a few hours on material science of batteries. But the short version is that by playing with the mechanics, we can make a solid state battery that is much happier, because we're not like pulling on the ceramic layers and causing them to crack. And when we've done it really, really well now, this is 400 cycles with basically no capacity fade, which is I think pretty significant. There's still some shortcomings, like, if it really worked this well in a commercial cell, I'd be rich. I wouldn't have to give talks unless I want to, blah, blah, blah. There's a long way to go. The capacity isn't high enough. Industry wants more. The current 1 milliamp per square centimeter means that this battery would take 2 hours to charge, which some applications could tolerate, but we've solved one of the problems, not all of the problems. So I just want to finish with lithium sulfur. I bring this up. I'm starting to write proposals in this area. I don't actually have any of my own work. This summer we started working on it. Nothing has worked so far. That's okay. It takes a little while. But I bring this up because lithium sulfur is how we could get from 300 or 500 to, a few thousand. So this is the kind of chemistry that would, say, give you the energy of a liquid hydrocarbon fuel in a similar mass. Will it be solved? I don't know. I hope to be part of the solution someday. But there's all sorts of challenges, and the commercial successes have been limited. Sodium sulfur is also, like, this is your lowest cost, because you just take salt water and take the sodium out. And you can see pyramids of sulfur from space, because there's so much sulfur that comes out of oil refining in Alberta. They have like pyramids of sulfur. So this battery, the materials basically cost zero. Again, this explodes sometimes. This explodes every time. So that's where our problem. But if we could get this, we get 400 increase. And so with this, you could fly airplanes. And the difference is in here, basically, in a lithium sulfur battery, you have pure lithium, that stores energy. You have pure sulfur, that stores energy. Here, I have one lithium and about 20 other atoms that do nothing. And so that's sort of the take home here. And the difference is the capacity here is thousands of milliamp hour per gram versus hundreds of milliamp hour per gram. So someday we might be there. I think there's still a lot of room in these systems, like 2x to 3x, but there's not the 10x that this might eventually give us. So, so what's my feeling, my opinion for light duty vehicles? We're going to meet the market needs for light duty, and yeah, we can keep getting a little bit better there. For heavy vehicles, look, Deere is making one of these autonomous tractors. But the cost and weight are still big challenges. I mean, Tesla's doing a lot with the Semi, mostly to drive around bags full of potato chips, so they don't care about the weight. But when they start taking rebar, we know that the numbers work. Aviation's got a way to go. We're really going to have to change. Rail, it's obviously very much a cost analysis. Some chemistries could do it maybe, but again, mass matters because you have to move it. So, lots of people. I had great collaborators here at companies, wonderful students, lots of people here at Illinois I've worked with, faculty and students. And, I think there's really opportunity still for significant advances in energy density. And thank you all. Really a pleasure to come here. I would love to open up the discussion.
Thanks. Well, this was great, and I do a lot of work at MRL, so I always feel guilty when
Keep coming.
I always feel guilty when I bring asphalt samples. Like, this is probably the dirtiest, most disgusting material they work with. But if you're working with sulfur over there, that makes me feel better because I've also worked with sulfur and I prefer the asphalt.
Right.
It's maybe a silly question, but I occasionally, because of my Google Scholar and ResearchGate notification settings, I occasionally get papers where they're using asphalt as an anode in place of the graphite in the battery. Is there any motivation or reason to use another kind of like carbon-based solid, let's say, at least at room temperature, in place of graphite there? Or, I mean, it sounded like you were thinking maybe towards other types of non-carbon.
Yeah, we're mostly thinking of silicon. I think that's, again, coming from the academic perspective. You can take coal, for example, and you can use, but unless it is fully graphitized right now, it only has about half the capacity of graphite. For sodium, it turns out actually you don't want graphite. You want materials that are less graphitic. And there have been talks about, should you be able to use things that are more like hard carbons? Interestingly, just yesterday, ExxonMobil bought a company in Chicago called Superior Graphite. And one of the reasons is that they are very interested in being able to use the pitch and other byproducts of the refining process as a feedstock towards graphite, potentially for lithium ion and other batteries. The big problem right now is the energy required to form graphite, and the temperatures are so high. There are some natural graphites, but very little in the US. So I think there's a lot of interest in an alternative carbon feedstock, and it comes down to your techno-economic. And for grid scale, maybe you'd say, I don't really care if the battery's 20% bigger if my carbon source was 50% less expensive. And it's interesting. I work with somebody at the Geological Survey that's also looking at coal-derived materials for energy storage.
You touched on some technologies that have been promised to us for like a decade and for more decades. And I watch a lot of stuff on YouTube, and the algorithm figured out that I like cars. So every once in a while I get videos like Panasonic came up with like a groundbreaking graphene, or CATL came up with a battery that just uses salt, or, as if this is something that's coming to market tomorrow. Are these like good products? Are they going to make their way into production, or is this just like hype?
It's mostly hype. There's always a little bit of substance to it, but I'd say there's two problems. One is that the incumbent technology continues every year to get better and cheaper. And so these ideas, they're like, oh, in 3 more years, we'll commercialize this. Well, the problem is in 3 years, the incumbent technology now has progressed to that point. Some of it is you really have to read between the lines. They say they use salt. Well, what do they really mean by that? And what are they going to pay in performance and system cost? I think the key lesson is that it's very, very hard to displace an incumbent technology. I mean, look, in microelectronics, they've been talking about replacing silicon since the 1960s. And the point is that, you look at that price curve, the battery now is half the cost of what it was 5 years ago. So all these things 5 years ago, they're like, oh, we're going to save so much money. And the energy density is 20% higher. And also the terms are very, very used. So when you hear solid state battery, there's a company, QuantumScape, that you may have heard of. Well, they say they're making a solid state battery. They're actually making a solid coating that goes on one side of the battery, and they still have a liquid electrolyte. And the market, for the most part, has been like, you don't really solve that many problems you don't solve a lot of problems unless you get all the way there. And, their stock price showed it. They were up at whatever, they're down at 2% of their peak because they have not been able to get in front of the market. And so, look, I have a lot of fun watching those things too, and one of them may be real.
I think we can take.
Yeah.
Thank you, Professor, for the presentation. I'm thinking from the transportation perspective, like besides the challenges of the weight and cost, are there any challenges related to the need to maintain those batteries during the life of a truck or plane?
Yeah. So there's a lot of interesting challenges with transportation. Some of them, of course, are a charge rate. In a lot of batteries, if you try to charge them too quickly, you actually form lithium dendrites, which can be catastrophic and lead to uncontrolled and unexpected failures. So rapid charging continues to be a challenge. That may be less of a challenge for the average consumer, but it may be more of a challenge for, road transportation of, heavier vehicles. Temperature is a big challenge. So to have maximal performance over a broad temperature range. And so, there's a lot of effort that goes into the thermal control of the battery. Not too hot, not too cold. If we could expand that window, it would actually save a lot of money from the standpoint. Prediction of battery life is improving, but I would say is not yet there, that there's still some noise. So it's a lot harder to do the analysis of, what is my full vehicle life and what's its performance going to be a decade from now. And so figuring out what you have in your fleet, repair. So yeah, look, in a just a normal person's car, these days an EV in a minor collision, they're just like, just total it. It's like, let's not take the chance. Or when there's a failure in the high voltage pack, they're just like, just remove the pack and put a new one in. It doesn't happen that much, that's okay. But particularly if you're in more aggressive environments, if you are in mining, if you're in other things, you might actually want to be able to fix, repair, deal with those kind of challenges, without tossing the vehicle or moving in what would now be $100,000 pack. Another area is sort of end of life disposal and use. The battery recycling industry is still sort of in its infancy. And can we do it? Can we do it responsibly? Can we do it economically? Is there a second life market or not? These are all unknowns that are much more difficult when you get past, middle upper class Westerners driving around their Teslas, where it's like, okay, whatever. So when you get to real nuts and bolts of making this work, it's hard.
We are out of time, but Professor's going to be here.
I'm going to stay here. Yeah.
So let's thank again Professor Paul Braun for his insightful presentation.
Thank you.
So, hey, Paul, I guess if they have questions here for 10 minutes.
Yeah, let's just hang out.
Guys, not just related to the presentation before I take them for a tour. If that's okay with you, Mariam. Okay. And it's gonna be